In 1948, a physicist named Maria Telkes had a radical idea. She set out to build a house in Dover, Massachusetts, that would heat and cool itself using almost nothing but salt. Through a remarkable natural phenomenon, the right kind of salt can soak up an enormous amount of heat during the day, hold onto it, and release it again once the air turns cold. Her project became known as the Dover Sun House, and at first it was a resounding success. The press called it the Model T of sun-heated houses, and popular science even boldly called it a more important scientific breakthrough than the atomic bomb. Yet within a few years, the project was quietly abandoned, and the idea of regulating a home with salt was all but forgotten. We're about to explore the strange story of cooling with salt and how you can put it to work to cool your home this summer. First, we need to understand what's happening inside your house on a hot summer's day. You see, heat moves into your home in three ways: conduction through solid walls, convection through moving air, and radiation pouring off the sun onto your roof and walls. On a hot afternoon, all three are loading energy into your house at once. Now picture walking into an old stone church on a scorching day. The air inside is cool, almost cold, with no air conditioning running anywhere. That's not magic you're feeling, it's mass. Thick stone takes a tremendous amount of energy to warm up, so it absorbs the day's heat slowly and barely alters the temperature inside. But modern homes do the exact opposite. We build with lightweight drywall, fiberglass insulation, and other materials that have next to no thermal mass. So when the sun loads heat into them, they warm up fast, the way a thin metal pan goes from cool to scalding in seconds. That heat penetrates through the thin walls and into the room you are sitting in. And all that unwanted heat gain arrives at the worst possible time. The sun peaks in the early afternoon, your walls dump that heat inside an hour or two later, and your air conditioner has to fight the overwhelming onslaught at once, during the most expensive, highest demand hours of the day. So if mass is what keeps that stone church cool, why not simply build with mass? Well, for thousands of years, that's exactly what people did. We raised walls of stone, packed earth, and heavy bricks, all chosen because they soak up heat and give it back slowly. But a material like stone can only store heat by getting hotter, which means it needs enormous volume and crushing weight to make any real difference. A wall thick enough to buffer a summer afternoon is totally impractical for modern urban worlds. But there's a class of materials that sidesteps that problem entirely. They are called phase change materials, or PCMs, and instead of storing heat by warming up, they store it by melting. And the one at the center of this story is Glauber's salt, a crystal of sodium sulfate mixed with water that melts at about 90 degrees Fahrenheit. And that can be tuned by blending in a measure of ordinary table salt to melt right in the comfort range of a room, around 70 degrees. And the potential for PCMs like this are huge. Pound for pound, Glauber's salt can hold up to 80 times more heat than brick, and it does it without warming up. The salt is sodium sulfate bound together with water into a crystal, and when that crystal reaches its melting point, it collapses, and the solid dissolves into its own water of crystallization. Breaking those bonds takes energy, and the salt draws that energy out of the surrounding air. As long as a single solid crystal remains, the temperature holds flat. Think of it the way you think of ice in a glass of water. As long as one cube is still solid, the drink stays cold, because the ice is spending the incoming heat on melting rather than on warming. And this was the exact principle Maria Telkes set out to harness back in the 40s. Telkes was a Hungarian-American physicist who had joined the solar program at the Massachusetts Institute of Technology in 1939. During the war, she had already proved she could put the sun to practical use, designing a small inflatable still that turned seawater into drinking water and went into the survival kits that kept downed airmen alive at sea. After the war, she turned to homes. Rather than fight the constraints of conventional thermal mass, she wanted to prove the potential of phase change materials, and Glauber's salt was her chosen tool. Together with the sculptor Amelia Peabody, who funded the project, and the architect Eleanor Raymond, who designed it, Telkes built what became known as the Dover Sun House in 1948, a venture carried, unusually for its time, entirely by 3 women. The house was a wedge-shaped, single-story home whose entire south face was a wall of 18 tall windows. Behind the glass, black painted metal sheets baked in the sun and heated the trapped air to around 100 degrees. Low-power fans then pushed that hot air into 3 insulated bins built into the walls, each holding a share of 21 tons of Glauber's salt. By day, the hot air melted the salt and the heat disappeared into it. By night, the fans reversed, drawing cool house air back across the bins, and as the salt recrystallized, it handed its stored heat back to the rooms. At first, the project looked like a resounding success. Through its first 2 New England winters, the house met 91% of its heating need from sunlight alone, with no conventional furnace running at all. The press flocked to it, and the Dover Sun House briefly became one of the most famous houses in America. But by its 3rd year, the system failed catastrophically, and the way it failed exposed the 2 flaws that kept this technology from becoming the standard for home construction. The first is phase separation. When raw Glauber's salt melts, part of it settles out as a dense solid that sinks to the bottom of the container and never fully recombines with the water above it. Cycle after cycle, less of the salt can reform, and its capacity bleeds away, falling by nearly half within a handful of cycles. The second flaw is supercooling, where the melted salt drops below its freezing point and simply refuses to recrystallize, leaving the thermal battery stuck as a useless liquid. And on top of both, the corrosive solution ate clean through the metal drums it was stored in. Within a few years, the house was switched over to an ordinary oil furnace, and the idea of a salt-heated home was largely forgotten. Although the Dover Sun House did not have the happiest of endings, it proved, however briefly, that a phase-change material has the real potential to govern a building's temperature with no mechanical system at all. And in the decades since, material science has caught up to Telkes' ambition. The fatal flaws of the Dover house have all now been solved. A pinch of borax gives the melting crystals a template to reform around, ending the supercooling, while a little clay or polymer thickener holds the dense salt in suspension so it can never settle, ending the phase separation. And sealing the salt in plastic rather than metal fixed the corrosion problem. Breakthroughs, such as these, and many others, have allowed for the emergence of the next-generation PCMs in our homes. In controlled wall tests, adding a thin layer of phase-change salt, barely a quarter-pound per square foot, raised a wall's ability to absorb a heat spike by about 74%, soaking up the peak hour of solar load before it could reach the interior. In occupied buildings, passive salt panels built into walls, ceilings, and roofs have cut total cooling energy by anywhere from 15 to 45%. And because they swallow the afternoon heat and release it after dark, they shave peak electricity demand, the most expensive power on the grid, by as much as 57%. And when you compare that to the alternative, adopting PCMs begins to make a lot of sense. A central air conditioner costs $5,000 to $12,000 to install, draws 1,500 to 4,000 watts whenever it runs, needs servicing every year, and has to be torn out and replaced every 10 to 15 years. A sealed salt on a wall, on the other hand, requires no ongoing cost. It has no compressor to burn out and no refrigerant to leak, and once it is sealed, it requires no maintenance or operational effort at all. While the lab studies have proven the theory, plenty of real-world cases are already reaping the benefits. A flexible salt blanket sold under the name ENRG has already gone into more than 1,000 buildings. In one university engineering wing, sheets of it tuned to melt at 73 degrees were laid across the ceiling, and they removed the need for mechanical air conditioning in that space entirely, recharging each night on cool outside air. So the case for putting a phase-change material system into your home is a strong one. The question is how. And the first thing to know is that this is not a solution for every climate. For the PCM to work, it has to fully refreeze every night, which means the outdoor air has to fall below its melting point, around 70 degrees, for several hours after dark. In a dry climate with cool nights, that happens on its own. But across the humid Gulf Coast and the Deep South, where summer nights often stay above 75 degrees, the salt never gets cold enough to refreeze. It sits there as a fully charged liquid with nothing left to absorb the next day, and without mechanical help, a passive salt wall in those regions simply does not work. Where the nights do cool off, though, there is a real and buildable project here. If you are still in the planning or building stage of a home, that is the easiest moment to incorporate it, because the material can be built straight into the walls and ceilings before they are closed up. The simplest path is to buy it ready-made. A company called Phase Change Energy Solutions sells flexible panels under the ENRG name, designed to be stapled inside walls or laid above a dropped ceiling. They run roughly $3 to $4.50 per square foot, more than ordinary insulation, but a one-time cost with no running expense behind it. An important caveat to utilizing a PCM for cooling your space is allowing the material to dump its heat at night to be ready for the next day. That means opening the windows. Glauber's salt only recharges on cool night air, and trapped in a warm room, it stays liquid, and by morning, the cooling system will be ineffective. While we're still in the very early phases of this technology, phase-changing materials are one of the most exciting developments in passive climate control, and one that will likely shape the future of our home in the decades to come. If you enjoyed this video and want to learn about other clever passive systems that can regulate the temperature of your home, then be sure to take a watch of our complete guide on how to build a passive cooling house next.